Energy-efficient system design for wastewater treatment plants. System splitting with an adaptive master controller. Energy is the largest component of operating costs at most wastewater treatment plants, and aeration equipment is by far the largest power consumer. So even a modest improvement in blower system efficiency can significantly reduce operating expenses. Even with advances in blower technology, system efficiency gains have been modest. A big part of the problem is the need to install a blower system that will meet increasing plant demand projected over 10, 20, or even 30 years. On top of that, treatment plants face daily and seasonal variations in air demand. So many aeration systems have been designed with very large blowers that run well below their best point of efficiency most of the time, and the benefits of more efficient blower designs are lost. To reduce the inefficiency of running oversized blowers, many are controlled with variable frequency drives. This has reduced the need to periodically change pulley sets and increase flexibility, but the efficiency of the blowers often varies widely at different speeds. The purchase and repair costs of large VFD units are very high. The drives often require engineering and on-site integration, so VFD units can greatly increase installed costs. Without any supervisory control, multiple VFDs may fight each other and cause unwanted swings in flow. To meet the challenge of efficiently producing air to meet varied flow demands, we suggest a system splitting approach. An efficient split system uses one VFD unit for trimming and multiple fixed-speed units for base loads. By reducing the number of VFDs, you reduce not only the initial investment costs, but also recurring energy and maintenance costs. In some cases, a second VFD may be desired for backup, but only one should run at a time. With some thoughtful planning, units can be sized to maximize utilization and result in average savings as much as 30% when compared to traditional system design. Select units that have as flat a performance curve over varying speeds as possible. And to prevent control gap, size VFDs with a control range that exceeds the flow of the fixed-speed blowers. While the VFD will likely run much of the time, the fixed-speed machines should be the workhorses of the system, with the VFDs smoothing out the small variations in demand. Properly sized machines can be placed in a short idle or standby state for rapid response to varying demands. A machine in idle will use far less energy than a loaded machine venting unneeded air, and will use no energy when turned off. Choosing energy-efficient blowers is important, but the critical element of this solution is an adaptive system controller. This smart device is programmed to select the appropriate units to bring online to meet demand most efficiently, based on an input signal, such as dissolved oxygen level. Programmed with each blower's capacity and power consumption data, it is able to monitor trends, unit performance, hours of operation, and overall power consumption. The adaptive controller can select from different size blowers based on the rate of change in the input signal and can learn patterns of system operation. The result is higher energy efficiency with minimal operating hours on each blower. With aeration being the highest energy consumer and energy being a huge portion of plant operating costs, good system design is essential. System design must go beyond the selection of blower units with efficient technologies. The blowers must be sized and controlled in concert to operate within their optimum speed ranges. Far too many blowers fail to meet their promise of efficiency because they are sized to operate in one set of conditions, but usually run in another. System splitting with adaptive control reduces both electrical and maintenance operating costs, and may even reduce the initial investment cost as well.